Good morning, class. All too soon, we've come to the end of this amazing course that is Applied Business Forecasting. My name is Bismarck Blay, and I would be presenting on the topic Analysis and Prediction of Electric Power Consumption in Tetuan, a city in Morocco. So I have a background in electrical and electronic engineering, so always excited to carry out prediction and analysis towards that direction. Problem statement. So Tetuan faces increased energy demands. Understanding factors influencing electricity consumption is critical for its efficient distribution and planning. And some of these factors are temperature, humidity, wind speed, and other environmental conditions. Now I have power distribution across three zones, and I have been able to divide them into zone 1, zone 2, zone 3, representing particular sections of the city. Now, this project aim to investigate these factors to predict energy consumption and also provide insight for better resource allocation by its local utility provider called Amendis. My data set has 52,416 observations recorded every 10 minutes, describing weather conditions and power consumption across three zones, that is zone 1, zone 2, zone 3. And these are some of the variables: data time, temperature, humidity, wind speed, general diffuse flows, and the three zones. Hypothesis and suggested methods. The first one is weather patterns, temperature, humidity, wind speed collectively impact power consumption differently across these three zones. Is it true? So the reason I had to use multiple regression analysis, initially I wanted to use factor analysis for this particular hypothesis, but I realized factor analysis requires a larger number of variables, which I have a couple of them. So then why not go in for multiple regression analysis? The second hypothesis is power consumption in certain zones is higher during specific times of the day due to peak usage patterns. Is that true? Now I have decision tree as my method, and at the end of this project or at the end of this presentation, you are going to know if it is true or not. All right, so still on hypothesis and suggested methods. The last one, or the last hypothesis, is seasonal variation significantly influence power consumption trends in Tetuan. And the method for this hypothesis is time series analysis. At the end of the presentation, we are going to know if indeed my analysis supports or rejects this particular hypothesis. Yeah. So the next slide is results and discussions. Now, the results and discussions is basically trying to bring the outcome of everything that I did in R. Yeah, that is what we are going to discuss here. So on the table, you see I have measure, value, and interpretation. You see, so this measure, let's say if I take the coefficient for temperature, I have a particular value that is 294.35 units, and also the interpretation. What you see there means for every 1 degree Celsius increase in temperature, power consumption in these three zones increases by 294.3 units. The same thing applies to coefficient of humidity and coefficient for wind speed. But don't forget that we have negative values for these two. This means that in every 1 unit increase of, let's say, humidity or wind speed, the power consumption in these particular zones decreases. So it means temperature is the only sole predictor in the increase of power consumption in these three zones. But at the end of the day, these three factors are contributing to the power consumption in this particular city or this particular zones that we have. And this is the result and discussion for the decision tree. So in the figure above, you could see that we have a decision tree and we have a lot of branches that is on the left side and the right side. Now, the first one, that is the 18E plus 3 that you see, is called the root node. Now, the root node has been splitted into two branches, And this root of the 3 is split based on temperature. So if the temperature is less than 24 degrees, the power consumption is around 18 million units, that is 100%. If the temperature is greater or equal to 24 degrees, the model suggests that power consumption will likely be lower, that is around 25 million units, 18%. On the left branch of this decision theory, I have temperature less than 22 degrees Celsius. And on the right side of it, I have temperature greater than 24 degrees Celsius. On the right side of the theory, when temperature is greater than or equal to 24 degrees Celsius, power consumption is higher. So if you have a lot of understanding or a bit of understanding on decisions theory, you see it makes it so exciting and interesting in the prediction of whatever that we are doing. Now, the results support hypothesis 3 as the decision theory reveals distinct thresholds like temperature, wind speed, and humidity significantly influence power consumption patterns in TET1. Alright, so this is the result for the time series analysis that I carried out. And from the time series analysis, I can confidently say that summer months may show higher power consumption due to air conditioning. And the reason why I have these higher figures during the summer month is because during the summer month, it is all places are heat up and automatically people will be on, and so we have a high demand on power consumption as compared to the spring that is a bit lower consumption due to mid-weather. Now, winter months also have moderate to high consumption linked to heating devices. So if it is snowing and it is cold, you will definitely go on your heater. So it also has an effect on the power consumption in TET2. All right, so conclusion, a positive correlation was found between temperature and power consumption, with zones showing varying degrees of sensitivity. Another conclusion or another thing I can conclude is seasonal trends were significant, with higher consumption in summer and winter due to cooling and heating demands. Yeah, and that is true from our analysis. We saw that. Now, peak usage times were identified varying slightly across the zones, but generally aligned with daily activity patterns. Now, this is what I have to say. Energy providers can use this insight to optimize resource allocation, plan for peak demand, and improve the power satisfaction of TET1 in Morocco. These are some few references. Thank you.